Okay, in this video, I'm going to give you an introduction on Mealy machines. We'll also look at the mathematical definition of a Mealy machine. Remember, a Mealy machine is very similar to a Moore machine. In fact, we can even convert a Mealy machine to a Moore machine, and also the other way, that is Moore machine to a Mealy machine. Again, we'll also look at a bunch of problems, which are very interesting problems, which can be solved using Mealy machines. Now, a Mealy machine is very similar to a Moore machine. The only difference here is that the outputs are associated with the transitions in a Mealy machine, whereas the outputs were associated with each of the states in Moore machine. Okay, so here what we are going to essentially do is that we are going to associate our outputs with transitions. Let's look at the FA given here, and let's convert it into a Mealy machine. So let's say my output generated upon transition B on Q0 is going to be 0. And similarly, the transition transition from Q0 on A, the output generated is 1. Similarly, at Q1 on A generates an output of 1. And Q1 on B goes to Q0 and generates an output of 0. So I'm just going to represent the outputs along with the transitions. So the outputs are always associated with the transitions. So this is the key difference of a Mealy machine compared to a Moore machine. And if you look at the mathematical definition, it's going to be the very same mathematical definition that we have seen. So let me write it down. Now, in this mathematical definition that you see here, again, Q represents the set of states. Q represents the set of states. Sigma represents the alphabet set. Q0 is representing the starting state. And again, here, delta is a function defined in the same way as that of a DFA. So it's a function defined from the cross product of Q and sigma to Q itself. Okay, this is the same definition that we have also already seen in the Moore machine. Okay, so this you have to remember. And again, lambda, you have another function called lambda again here. So lambda is a function which is defined from Q, that is the set of states, to the set of outputs. And remember, delta is the set of outputs. So set of outputs. So everything remains the same as that of a Moore machine. The only practical difference here is that all the outputs are associated with transitions. Okay, so that's a key difference that you need to understand, right? Now, if you look at the Mealy machine in this diagram, okay, you can see that on getting B's, you are outputting zeros, and while on getting A's, you are just outputting ones. And if you look at Q0, on getting a B, your output is 0. On getting an A, your output is 1. Then if you're getting a 1, you're at Q1, and from Q1, if you're getting an A, again you're generating an output of 1. And if you're getting a B from Q1, you're generating an output of 0. So we can easily correlate with this example with the same example that we have discussed while we designed Moore machines. So this is a Moore machine which is going to count the number of A's. It's going to count the number of A's in the given string. Okay. So we will also design some more Mealy machines. In fact, we can design Mealy machines for all the problems that we have designed Moore machines, and we'll look at some more problems for designing Mealy machines. Again, here is one very important thing to remember here is that in Moore machines you had a default output. Okay, so if you look at the starting state here. Okay, so in Moore machine there was an output associated with the starting state, but here in Mealy machine you will get an output only upon transitions. Okay, So it's very key to understand. It's very important to understand that if you give an epsilon string, okay, so which means an empty string. So if your word is an empty string, okay, so I am giving an empty string as an input to this Mealy machine, okay, so it cannot generate an output here. Whereas in a Moore machine, an epsilon string can also generate an output, which was there in that, which was represented at the state Q0. But here, since we define outputs only upon transitions, an empty string does not make sense. So if you give an empty string to a Mealy machine, it will not produce an output. Okay, your output will be empty. Okay, so this is also very very important to understand. And therefore, for the same reason, if a Mealy machine is given with n inputs, okay, n inputs are fed into a Mealy machine, you can understand that it will generate exactly n outputs. Okay, so this is the case of a Mealy machine. So we already encountered the Moore machine where n inputs, n inputs will mean if you're given n inputs to a Moore machine, it will generate n plus 1 outputs. Okay, we have already encountered this. Okay, so this was applicable for a Moore machine, but whereas for a Mealy machine, if you give n inputs, you will get only n outputs. This is because you don't have a default output here. But whereas for a Moore machine, you have a default output which is present at Q0. So suppose that you have an output X associated with Q0. This is always, the X output is always going to be there in your output. That's why you have n plus 1 outputs here. Whereas for a Mealy machine, you will always have n outputs if you have n inputs. Now let's solve some problems related to the construction of Mealy machine. So if the first question is to count the number of occurrences of 0 in a binary string. So this is going to be very straightforward. So upon in your starting state, you can either see a 0 or a 1. Okay, so you are asked to count the number of zeros. So whenever you see a 0, you have to output 1, right? And whenever you see a 1, you have to output 0. So that's going to be very straightforward. So just define a transition saying that whenever I see a 0 in my input string, I'll be providing an output of 1. Similarly, whenever I see a 1 in my input string, I will be providing an output of 0, right? So this is how it's going to work. So let's look at an example how a binary string will be processed. So if you're given with a 0, 0, 1, 0, right? So if you give this input to this Mealy machine, what will happen here is that the output will be generated like this. So for 0, so when you see a 0, 1 will be generated. Again, when you see a 0, 1 will be generated. So now you are seeing a 1, so a 0 will be generated. And when you see a 0, again a 1 will be generated. So if you count the number of ones here, okay, if you count the number of ones in this string, you will get 3, and 3 is the number of occurrences of 0 in this binary string. Okay, so this is a very simple question. Now, if you look at the second question, it is about counting the number of occurrences of AB as a substring where the alphabet set is A, B. Now, the design is very straightforward here. So if you see a B in the starting, then you are going to output a 0, right? Now if you see an A, still you will output 0, but you will go to another state, that's Q1. And from there, if you see a B, you can output a 1, right? Okay, so again, if you see A's continuously at Q1, you will still generate 0. Okay, So if you see a B, that means you have seen an AB pattern. Okay, so if you see a B from Q1, you are going to generate a 1. Okay, so I think we have completed all the transitions from all the states, right? So there is a transition A and B from Q0. There's a transition on A and B from Q1, right? So if you look at, you can actually give a sample string, like say A, B, B, A, B. Okay, so if you parse this string using this Mealy machine, you can understand that the Mealy machine will give you 2 ones in its output string. So you can actually run through. You can actually parse the string using this Mealy machine, and then clarify that. Now let's go to the next question. So the question is, generate the ones complement of a binary string. So we have already designed the Moore machine to generate the ones complement of a binary string. So it's here it's going to be again simpler. So we'll start with the starting state, say Q0. Okay. So as per the definition of ones complement, if you see a 1, you have to output a 0, and if you see a 0, you have to output a 1. So it's going to be very simple. So what you need to do here is that if you see a 1, you have to output a 0. And if you see a 0, you have to output a 1. That's it. So in this question, you are asked to generate the 2's complement of a binary number. So you might have already studied how to find the 2's complement of a binary number in digital systems, right? So I will just recap you with an example. Okay, so you might be knowing that positive 10, that is the decimal number, has an equivalent representation of 0, 1, 0, 1, 0 in binary. So if you want to convert this into 2's complement, right? What you need to do here is that you have to invert all the bits. So it will be like 1, 0, 1, 0, 1, right? So this is the 1's complement of the given number. And now you have to add 1 to this. Okay. So once you add 1 to this, 1 plus 1 is going to be 0 with a carry 1. So it is going to be 1 here, followed by 1, 0, and 1. Right. So this is going to represent negative 10 in 2's complement. So this value that you see here is going to be the representation of minus 10 in 2's complement, right? Now this is the normal procedure that we apply to find the 2's complement of a given number, right? Again, there is a very ingenious trick for finding the 2's complement of a given binary input. Okay, so if you know that trick, then creating this Mealy machine will become more easy. So let me tell you that. Okay, so again, the given input here is that 0, 1, 0, 1, 0. Okay, so the trick is that you scan from the left side. Okay, so let me take my pointer, and then so what you're going to do here essentially is that you're going to look at the input from this side. Okay, and what you're going to do is you parse, go through the number until you get a 1. Okay, so in this case you're getting a 1 here itself. So what you're essentially going to do here is that you're going to copy all those until you see a 1. Okay, so you're going to copy this 0. You're going to also copy this 1. So until you see a 1, all the inputs are copied, including 1, right? And then what you're going to do is you're going to reverse or invert the other values. So 0 will become a 1, 1 will become a 0, and 0 will become a 1. Okay, so you can compare the answers now. Okay, so by using this trick, we got the very same answer, 1, 0, 1, 1, 0. So here also you got 1, 0, 1, 1, 0. Okay, so the idea here is that you scan the string. You scan the string from the left side. Okay, and what you do is go till you see a 1, and including that 1, copy everything, including that 1, and to the left of 1, whatever you see, just invert those bits. Okay, that's the idea. So using this idea, using this trick, you can actually find the 2's complement of a given number. Even you can also apply the 2's complement of a 2's complement to get back the number itself, right? So let me show you that also. So it will become interesting. So if you apply the same trick on this number, on this 2's complement representation, we are expected to get this result back. Okay, that is 0, 1, 0, 1, 0. Okay, so let's try that. Okay, so if you scan from this side, so this is a 0, you have to just copy it, and here you see a 1. Here you see a 1, just copy that. And after that, you have to invert. That means this 1 will become 0, this 0 will become 1, and this 1 will become 0. So you can see that you're getting back what we started with. So this was our original input that we started with. So remember, 2's complement of a number, 2's complement of 2's complement of a number gives the number itself. Okay. So this trick for finding the 2's complement can be applied while designing the Mealy machine for generating the 2's complement of a binary number. So this is not a very trivial question. You should know this trick. Okay, so this trick of converting a binary number into its 2's complement. Then only you can attempt this question, right? So what we are essentially doing here is that until you see a 1, okay, so you parse the string until you see a 1, and up to that portion you are going to copy everything as it is. And then when you see a 0, you're going to output 1. Then when you see a 0, you're going to output 1. When you see a 1, you're going to output 0, and so on, right? So this is the trick that we are going to apply here. Let's look at one more example for more clarity. So if you're given with 0, 1, 0, 0, 0, okay, and you're asked to convert it into its binary, into its 2's complement form. Okay, so we can verify that the answer that you get is going to be 1, 1, 0, 0, 0. Okay, so in fact, this number actually represents positive 8, and this number in 2's complement representation would represent -8. And remember, for representing -8, 4 bits are sufficient. 1, 0, 0, 0 is sufficient for representing -8. So this 1-bit extension is something which we have already studied as a Sine extension. It happens because of Sine extending. It's called Sine extension. Okay. So anyway, so if the input is 0, 1, 0, 0, the expected output is going to be 1, 1, 0, 0, 0, right? So we are going to use this example while designing our Mealy machine. Okay. Very importantly, you have to remember that you have to feed the input from this side to this side. Okay, that's how we are designing it. Okay, so even though your input is 0, 1, 0, 0, 0, you're going to feed to the Mealy machine in a reverse way. That is, you're going to feed it like this: 0, 0, 0, 1, and 0. So because our operation is like that. Okay, so that's very important. So remember that you're going to feed this in the reverse manner. Okay. Okay, so let's get started. So let's start at Q0, and remember, so until you are getting a 1, so whenever you are getting a 0, you're going to output a 0, right? So remember that we are scanning from left to right. So whenever we are getting a 0, our output is also going to be 0. And also remember, when we are getting the first one, okay, when we are getting the first one, again the output is going to be 1. And so whenever we get a 1, we are going to a new state, just because we want to have different transitions there. So from Q1, if you are already at Q1, then it means that you have seen a 1. Okay, so you have seen some when you're parsing the binary string, so if you're seeing at least a 1, you will be at Q1. That's the meaning. And if you're at Q1, so now what you're going to do is you're going to invert everything. So if you see a 0, you're going to output 1, and if you see a 1, you're going to output a 0. Okay. So if you look at this part alone, Q1. Okay, at Q1, what you're doing is just a 1's complement. You're inverting. If you're getting 0, you're making it as a 1. If you're getting a 1, you're making it as a 0. So before that, what we are doing in this part is just copying. Okay, so if you're getting a 0, you are outputting 0. If you're getting a 1, you're providing the output as 1. Okay, so now let's feed this input to this Mealy machine and find how it is going to work. So I'm going to write the outputs here. I'm going to write the outputs here. Okay. So as I said, we are going to feed the input in the reverse way. So we are going to feed this 0 first. So if you feed this 0, then at the output also we'll get. Look at here. So if you are feeding a 0, your output is going to be 0. Okay, so our first output is going to be 0. So now the second input is also a 0. Okay, so again 0 on Q0 on 0 again gives you 0. So the output here again will be 0. And this continues. Okay, so next one is also 0. You'll get the output as 0. Next you have a 1. Very importantly, next you have a 1. So what you'll do is you'll shift from Q0 to Q1. Again, note that the output here is 1. So you'll get an output here. In the output, you'll be getting a 1. Okay. So in the output, you'll be getting a 1. Now, since now you are at Q1. Now, since you are at Q1, what happens is that whenever you see a 1, the output is going to be 0. Whenever you see a 0, the output is going to be 1. Okay, so in this case, we have already seen a 1, and we have the output is 1. And next we have a 0, so the output will be, so since next we have a 0, so this is a situation that we are dealing with. So since we have a 0 input, our output is going to be 1. So the output that we are getting is going to be a 1. Okay, so this is how we are going to get this. And remember, since we have fed the output in the reverse way, since we have fed the input in the reverse way, our output also has to be read in the reverse manner. Okay, so you need to read this in the reverse manner. That means you have to read from here to here. Okay, and so the output, when read from the left to right, it is 1 1 0 0 0. So that's the expected answer. Okay, so if you are reading this in this way, what we are actually getting is 1 1 0 0 0, and that's the expected answer, right? So in this case, in this particular question, very importantly, you have to know this trick. So the normal 2's complement method will not work out here. So if you know this trick of converting a given binary number to its 2's complement, then you can easily design this. Remember, this part is just 1's complement. Okay, this part is just 1's complement generation, and in this part, what you're doing is whenever you're getting a 0, you're just outputting zeros, and whenever you get a first one, you're outputting 1 and going to Q1, and from Q1 you are actually generating the 1's complement, and that's the beauty of it. And that's how we are going to get we are able to generate the 2's complement of a binary number. Now let us look at one more question. So in this question, we are asked to design a Mealy machine to perform a binary addition. The question can be also asked like this: design a binary adder using a Mealy machine. So we have already studied about binary addition in our digital systems. So binary addition is something which is very familiar to us. So remember, this question, the solution to this question is not very trivial. We may think that how can I give two binary number inputs to a Mealy machine? So the way this is solved is really tricky. So we'll come to know that there are few people around us who are really clever. Okay, so we could actually find a way to solve this. Okay, so if two numbers are given, let's quickly revisit the process of binary addition. Suppose you are given with 1 0 0 and some other number, say 1 0 1 0. Okay, so you may be knowing that this represents 4 and this represents 10, right? So what we are going to do is, when we are adding this, okay, so there are some rules for binary addition, so which you may be already aware. So let me list it down very quickly. 0 plus 0 is going to be 0. 0 plus 1 is going to be 1. Again, 1 plus 0 is again going to be 1. So 1 plus 1. Okay, 1 plus 1 is something which is you need to take care of. So this is we studied it like 0. The answer is 0, but with a carry of 0 with a carry of 1. Okay. So we have covered all the cases: 0 0 0 0 1 1 0 and 1 1. Right. So these are the rules for binary addition. Okay, so with that rules, if we apply on this, okay, so what we are going to do in the design of Mealy machine is that we are going to fill up the empty slots with zeros. Okay, so in this case we only have one empty slot here, because 4 is less than 10, and so 4 had an empty slot. So if there are no empty slots, okay, there's nothing to be done. So you make the numbers in such a way that both of them are having equal number of digits in it. Okay, and one more very importantly, you have to do one more thing, is that you have to append 2 zeros in the beginning. So this is a very important step which you need to remember. So the first thing is that you put additional zeros to balance the number of digits in both the numbers. That's one thing. And again, very importantly, you have to also put an additional zero to both of the numbers. So once you've done this, this is very important for performing binary addition using for designing. So if you want to design a Mealy machine for performing binary addition, so this is very important. So you'll come to know about it, why it is done when we go through it. So here if we apply the binary addition rules. So 0 plus 0 gives you a 0. 0 plus 1 gives you a 1. 1 plus 0 gives you a 1. 0 plus 1 gives you a 1. 0 plus 0 again gives you a 0. So this is going to be our output. Okay. So in this case, everything was very trivial. Okay, it was very trivial. So let's look at some more non-trivial example. Okay. So let's say our input is say 1 and 1 1 1. Okay, so we want to add 1, okay, with 1 1 1. So 1 actually represents 1 in decimal. 1 1 1 represents 7 in decimal. So as I said, we have to add empty slots with zeros. So you have to make them equal, to have equal number of digits. So we'll add 0 here, we'll add 0 here, so that both of them have become equal digits. And very importantly, you have to add an additional 0 to both the digits, and this is a very important step. Okay, so now let's perform the addition on these numbers. So 1 plus 1 is going to be 0 with a carry 1, right? So if you are having a carry 1, then your 0 plus 1 is not 1, because you have to consider this 1 as well, right? So that's going to be very important. So when we design the Mealy machine, you have to understand that even if you're having 0, 1 to add, but remember one is a carry for you. Okay, so your output should be 0 again with a carry 1. Okay, now again 0, 1 is not going to generate you 0, 1. Instead, you have to also consider the carry 1. So 0, even though the inputs are 0 and 1, but along with the carry, you are expected to get a 0 here. And now you have a carry 1 again here. Okay, so now when you add with 0, 0, so when you see 0, 0 in the next the last location, we are always guaranteed to see a 0, 0 because we added it intentionally. So what we are going to see is in the last place is going to be 0, 0. And this is the most important thing. So if you're having a carry when you are adding 0, 0, you are going to output a 1. So in this case, your output is going to be 1. So suppose if there are no carries, we know that 0, 0 is going to give you just 0. Okay. So if there were no carries from the previous state which is coming up, and then in that case you're going to output a 0. So in this case we have a carry 1, so that we are going to, even though our input states are 0, 0, we intentionally remember these 0, 0s were added intentionally. So we are guaranteed that the last input state, the last input is always going to be 0, 0. So if you get a 0, 0, and along with the carry, you're going to generate a 1 as an output. You have to generate a 1 as an output. And if the input states are input state is 0, 0 and there is no carry, then you can very easily generate a 0. So that's the idea that we are going to look into. Okay. Now remember that whenever we are designing a Mealy machine, we are going to look at the inputs in pairs. So if this is the question that's given, if this is the example, we are going to consider 1, 1 as our initial input. Okay, and then we are going to consider 0, 1, and then we are going to consider 0, 1. Again, at the last state, we are going to consider 0, 0. So we are going to consider the input in combinations, like so 1, 1, 0, 1, 0, 1, and 0, 0. Okay, so let's start designing the Mealy machine. Okay, so let's start at Q0. Okay, now from Q0, I'm going to write the transitions where carry is not applicable. That means I'm going to write this case 0, 0 generates a 0, 0, 1 generates 1, 1, 0 generates 1. So in this peculiar case is going to have a carry. So I'm not going to write that in my Q0. I'm going to write these three cases, all these cases where I don't have a carry. Okay. So let me write the transitions. So okay. So my inputs can be 0, 0. So let me first write the inputs and then I will write the outputs. 0, 0, 0, 1, and 1, 0. And the outputs, okay, so let me delimit it using a yellow color. And the outputs are going to be, in this case, 0, 0 generates a 0, 0, 1 will generate a 1, 1, 0 will generate a 1. Okay. Now we are left with one more possible input state, that is 1, 1. So so if you're getting a 1, 1, remember, if you're getting a 1, 1 from Q0, 1, 1 is going to generate the output as 0, but with a carry 1. So that demands us to move to another state, say Q1. Okay, so upon getting a 1, 1, I am going to move to Q1. Okay, and the output upon 1, 1 is known to us. It's going to be 0. It's going to be 0. It's going to be 0 with a carry 1. So remember very importantly, whenever I get a carry, I am at another state called Q1. Now you can understand these two states, that's Q0 and Q1, as Q0 is a state where you don't have any carry. So I can write it as a non-carry, non-carry state, non-carry state, and Q1 is going to be a carry state here. So Q1 is a state where you have a carry. So Q1 is going to be a carry state. So remember, so when you write the rules of binary addition, so if you're writing the rules of binary addition in a non-carry state, you're assuming that you don't have a carry with you. But whereas at Q1, you know that you are, that the carry is there, and then when you write the rules of binary addition, you also have to add that carry. For example, so if you want to define the rule of addition for 0, 1, okay. So we know that 0, 1 will generate normally if it is not, if we are not considering a carry, 0, 1 combination will generate 1 as the answer, 1 as the output. But since we have a carry, we have to add that also. So when we add 0, 1 plus the carry, then we will get 0 as the output. Okay, remember our output here is going to be 0. That's very important. Okay, this is because we also have to take care of the carry. Okay, now since we are adding 0, 1 with a carry 1, then we are getting 0 again with a carry 1. Okay, remember your output is 0 again with a carry 1. So you have to go back to Q1 itself because you are still in the carry state. That's why upon 0, 1, I can just come back. The transition is going to be going back to Q1 itself. Okay, so that's going to be very important. So upon 0, 1, I am going to Q1 itself because still I have a carry. Okay, so what if I have a 1, 0 in my input? Again, remember 1 and 0 normally will give you the output as 1, but since you have a carry, your output is going to be 0 with a carry 1. Okay, since again you have a carry, you again go back to Q1. So upon seeing 1, 0 also, you're looping back to Q1 itself, right? Now what about 1, 1? So if you perform 1, 1, what will happen? So suppose if your input is going to be 1, 1, okay, this is going to be very interesting. Okay, so once you have a 1, 1 in your input, remember you also have a carry. Okay, so your output depends on the addition 1 plus 1 plus 1, because you have a carry, that's 1, and in your input you have a 1, 1. So this is going to be 1 with a carry 1. Okay, 1 plus 1 plus 1 is going to be 1 with the carry 1. Okay, so 1 with carry 1. So this rule is also very important. So this rule is very much applicable when we have the input state as 1, 1, when we have the input state as 1, 1, and the carry is 1, right? So this rule is very important. So here again we know that the output is going to be 1. The output is going to be 1 again with a carry of 1. So in this transition, this also goes back to, so there are 3 cases which goes back to Q1 itself, because in all these 3 cases, that is 0, 1, 1, 0, 1, 1, you still have a carry. That's why you are looping back to Q1 itself. Okay, that's very important. And what if your input is 0, 0? That's a very interesting case. Now if your input is 0, 0, the output is going to be 1. But remember, we don't have a carry. We don't have any further carries this time. That's very important. So let me write it here. If your input is now, if your input is say 0, 0, okay, what do you have? You have in your output as 1, because you have a carry. So the real addition that happens here is your carry plus 0 will give you a 1, right?
and now you don't have any further carries. Okay, so that means you have to, you can move to the non-carry state. Okay, from now on, from now on, if you move to the non-carry state, okay, so upon getting a 0 0 from Q1, you have to actually make your transition back to the non-carry state, right? This is a very important thing that you need to remember. We are doing this because when we are performing the 0 0 binary addition with carry 1, we are getting the output as 1, but but at this time we don't have a carry. Okay, so that's why very importantly we have to shift to a non-carry state. Okay, so that's going to be very important. Okay, so whenever you get a 0 0, you are moving back to the non-carry state. And remember, from Q0, when you're getting 1 1, okay, you're going to have a carry. That's why you're moving to Q1, right? At Q1, if you're getting 0 1, you still have a carry. Okay, that's why you're staying at Q1. You're looping back to Q1 itself. At Q1, if you're getting 1 0, again you are staying at Q1, just because you're again having a carry. If you're getting 1 1, your output is going to be 1 with a carry 1, and that's why you are staying at Q1. So for all these three input states, the transition is going to go back to Q1 itself. Okay, but for 0 0, remember, very importantly, for 0 0, whenever you get a 0 0, you know that since we have a carry already, the output generated is going to be 1, and very importantly, there are no further carries. That's why we are shifting to the non-carry state, right? So that's how this machine can be designed, right? Now let's look at how this machine can process a given input. Okay, let's look at this example itself, the example which we already started off with. So let's see this example itself. Okay, so initially we have 1 1 in our input. So supposing that we are at Q0, so when we get a 1 1, we are actually going to output 0. Look at here, our output is going to be 0, and then we are going to Q1. That's the first thing that will happen when you process 1 1. So let me write the outputs. Let me also write the outputs in yellow color, right? Okay, so upon seeing a 1 1, you are going to generate an output of 0, and then you will be at Q1. Okay, so now you are at Q1, and the next input that we have here is 0 1. Okay, so look at the output here. 0 1 generates 0, and again the transition is going back to Q1 itself. So you are at Q1 after generating the output 0. So let's write down the output. Okay, so again you're getting a 0 output. Now again look at here. So the next input is also 0 1. The same thing will happen. So you will generate an output of 0, and you'll stay in the same state, right? Now look at the next state. It's going to be 0 0. Oh, so this is where the transition happens. Transition will go to Q0 back. Okay, so here, look at here. When you're getting a 0 0 in your input, you're going to generate an output of 1, but you're going to move to Q0 itself. Okay, so that's very important. So now, since you're seeing a 0 0, your output is going to be 1, but now you are at Q0. Okay, so we can verify that the answer that we have done manually matches with the answer that is given by the Mealy machine. Okay, you can also try out by extending the question. Okay,
so let's say I want to extend this question. Say I want to add 1 1 0 0 0 0 1 to 0 0 0 1 1 itself. Okay, so remember this number that I've modified here, that is
1 0 0 0 1 is going to be this is going to be looks like 17, right? This is going to be 17, right? And for the second number, I have not made any modifications, right? It's going to be 7 itself. So 0 1 1 1 is going to be 7 itself. Now the first step here is to fill the empty slots with zeros. So I'll be putting a 0 here, right? And very importantly, you have to add a pair of zeros in the beginning. So this step is very important before putting your strings into the Mealy machine. Okay, so if you're not taking care of this step, there can be errors in your output. Okay, so you have to actually prepare your inputs before actually putting it in your Mealy machine. So now let's work out this question now. So up till here everything, so whatever we have found up till here, everything is going to remain the same. So you'll get 1 0 0 0 in the very same way. And now remember, whenever we saw a 0 0, so in the earlier question, whenever we encountered a 0 0, we moved from Q1 to Q0 and producing an output of 1. So now we are at Q0, right? So at Q0, if you see a 1 0, okay, so you're at Q0 means you're at a non-carry state, and at Q0, if you see 1 0, then you're going to generate a 1, right? So your output generated in that case is going to be 1, right? Now moving further, so finally you have a 0 0 here. Now again you're at Q0. 0 0 on Q0 will give you the output of 0. So let me write down 0 here. So this is going to be your output. So you can actually verify that this is nothing but 24. That is 17 plus 7, right? So given two binary strings, you can always perform the binary addition, by adjusting the input strings, by putting some additional zeros to fit in for our Mealy machine. And the Mealy machine always will generate a binary binary. It will function like a binary adder for us, right? Remember that this design is a very non-trivial design. So if you don't know how to don't know this method, it is not very trivial to design this. It's not very straightforward. Okay, so it means that if you could design this without knowing this method directly, if you could design this, then it means that you're a kind of a genius. Okay, so that's why I took a lot of time explaining this. Okay, and remember that since we have designed a Mealy machine, okay, so we can actually convert a Mealy machine. We can actually there are methods to convert a Mealy machine to a Moore machine and back. Okay, so which we will learn later. So a Mealy machine can be converted to its equivalent Moore machine, and similarly a Moore machine can also be converted back to a Mealy machine. So they are equivalent, right? So if you're comfortable in designing Mealy machine, you can actually convert it into its equivalent Moore machine very easily. The conversion of Mealy machine to Moore machine is not a very difficult task. It's a very straightforward task. The only thing is that you have to follow some sequential steps. Okay, so the Moore machine to Mealy machine conversion is also very similar. So they are straightforward processes. So if you know how to design a Mealy machine for a particular problem, right? So what you can do, if in your question you are asked to design a Moore machine, you can actually design a Mealy machine and then convert it into Moore machine. Okay, so in this case, in this question, in the question of designing a binary adder is comparatively easier using a Mealy machine.
Okay, so the process that we have done is comparatively easier than designing a Moore machine straight away, right? So if the question is if in a given question, if you're confident enough to design a Mealy machine, and in the question if you're asked to design a Moore machine, what actually you can do is you can design a Mealy machine and then convert it into a Moore machine. Okay, so we'll learn the conversions in our next video. Okay. Now, as an assignment, you can design the Moore machine and a Mealy machine to count the number of occurrences of the substring AAB, where the alphabet set is A, B. Similarly, you can also try to design a Moore machine to find the 2's complement of a binary string. So we already designed the Moore machine the Mealy machine to find the 2's complement. Okay. Similarly, you can design a Moore machine to perform binary addition. Okay. So here you're asked to design a Moore machine. Okay. So we have already designed the Mealy machine for the same question. So applying the same principles and methods, you can try to design the Moore machine for finding the 2's complement, as well as to design a binary adder using a Moore machine.